Hello everyone, this is Professor DePaula. Welcome you back to Psych 220 Behavioral Statistics Online. And in this week's lesson, we're going to be talking about distributions, more specifically frequency distributions or distributions of scores, and how to construct them and the various shapes that they can take on and why this is a useful exercise when we're looking to describe the data. So in this chapter, we're going to be talking about why we need to use frequency distributions, why they're important. We're going to look at how to organize data into a frequency distribution table, very simple table, and also into a group frequency distribution table. And most of the time, we're going to be using grouped frequency distributions just because the number of values we have is very large in the amongst the variables that we collect and we record. Then we're going to look at how to interpret these frequency distributions. That's in terms of looking at shapes of the distributions and what happens if the distribution is symmetrical versus skewed, and what the effect of outliers could be, what the sort of interest in these outliers could be. Could they be fake data, entry errors? Could they be people lying to you on your surveys or exaggerating certain things? So it's important to sort of recognize that a few data anomalies, what we call outliers, could have a variety of causes, and they can influence what you do with the data moving forward. Then we'll talk about how we'll organize the data into frequency distribution graphs, which are mainly histograms that we use to look at the shapes of the distributions, although you can look at frequency polygons as well, and how to interpret these graphs, and how people use graphs to kind of lie to you or manipulate you in certain ways to get their point across. So a frequency distribution is just an organized tabulation. It's basically a table of values or ranges of values that your data can take on, whatever variable you're measuring, and you could be measuring many, many variables, and you would have a frequency distribution for each variable that you're measuring. And based on the frequency distribution, you can find out how many people in your sample size, your N, right? What their scores are there any anomalies or outliers, and what do those outliers tell you about the data being collected? You can also look at the levels of measurement, the scales of measurement as well. This can be set up into either a table or a graph. A lot of times I like to look at both. I like to look at the frequency distribution table to see if there's any errors in the data entry or data recordings, any outliers, any really patterns that kind of stand out for me and say, wait a minute, something's going on here, or I don't like this, or this is interesting in some way. And then a graph. And we can make a table and a graph on the computer in a matter of seconds. Most of this stuff is done on the computer, but we're going to be going through if you were to manually do a very simple thing, just because when you process things manually and you learn things by hand, the concepts tend to stay with you longer. Rather than just say, okay, we do this in a computer and we hit a button and it shoots out the answer. Then the computer becomes like a magic box. Like you just hit a couple buttons, a couple menus, and then you get the answer you want. And you're not really understanding what's going on with the process. So doing things by hand helps you understand the process more than just doing it by the computer. The computer's there. I use the computer all the time, but I've also done everything by hand first. So I understand the process, and now I can then use the computer effectively. Frequency distribution tables are usually in a column format. So you have the values in the left margin of the table listed, or you have a range of values listed. And then you have in the table, you have a frequency column where you list how many people are in each category or each bin. So how many people scored a particular score, or how many people scored within this range of scores. And you'll have a frequency or an F column for that. Then generally you'll have a proportion column, or some people call it a relative frequency column, which tells you what proportion of the total sample is in each interval or in each or has each particular value. And then you could go from there. You can have percentages, you can have cumulative frequencies, you can have all kinds of things going on from the cumulative percentages. We're going to keep it really simple for this class, considering it's online. If the class was in person, I would be doing a little bit more in-depth, probably processing of how to make a table. But since everything's online, it's it's not as convenient. I can't just show you exactly what I'm doing, although I can try. It's not as easy as going to the board and writing it out. So we're going to keep it relatively simple, but you'll get the gist and the main point of it. One thing you need to know is that the sum of all the frequencies will equal n. So sum of f equals n. The sum of all the frequencies gives you the sample size, the total sample size, which is capital N. And if you want to compute the sum of x from the table, you could either write out all the original scores, which might take a long time. I don't suggest doing that, or compute the sum of f times x. So basically, you take each value, which is your x, and each frequency, and you multiply them together, which is f times x. So if you had a score of 4, and you had 3 frequencies having a score, or 3 people had a score of 4, you would take 4 and multiply it by 3, and you would get 12. And then you would add up all those totals. So you would multiply each value of x times its corresponding frequency, and then sum up all of those products. And that would give you the total sum of x. So sum of x is relatively easy to compute from a frequency distribution table. We can also convert our frequencies into proportions, which are known as relative frequencies. All we do is take the frequency for each category, for each value or values, value if you have a single value table, and values if you have intervals in your table, what's called a grouped frequency distribution. You take those frequencies and divide it by n, the total sample size, and that gives you a proportion, which we're calling small p. And the proportion is the same thing as a relative frequency. So you may have heard in other classes relative frequency, that's this. It's just f divided by n. The text is calling it proportion, but it's also saying it's relative frequency. They're interchangeable. That's what is the proportion of total cases in each category. That's your proportion or relative frequency. And if you multiply that proportion by 100, you get a percentage. So that gives you the percentage of each category that's, the percentage of the total sample size that's represented in each category. So you take that proportion, you multiply it by 100, you convert the proportion to a percentage. That's all it is. And you can make a column called percentage in your table if you want. Just multiply the proportion or the relative frequency column by 100. Very simple to do. So here's what it looks like. You see several values. So we had a value in this. So this variable had 1, 2, 3, 4, 5 different values. So there was a value of 5, a value of 4, a value of 3, a value of 2, and a value of 1. So there's 5 possible values that your variable can take on here. Now, normally in real research, you're going to have a lot more than that. But for simplicity's sake, let's start out and just say that whatever variable you're measuring, you only have 5 different values. So those are your x. X is what are your possible values here? And this is discrete. This is a discrete variable, which means there's no intermediate values, right? So you could either score a 5 or a 4 or a 3 or a 2 or a 1. You can't score a 5.12. You can't score a 3.56. There's no intermediate values. There's only 5 finite values. So this is termed discrete. This is a discrete variable. You have a very limited number of values. There's no intermediate values here. So this is a really simple example because you're using a discrete variable with only 5 different values. Now the F column is the frequency. So this states that one person scored 5, 2 people scored 4, 3 people scored a 3, 3 people scored a 2, and 1 person scored a 1. Now if you add up this frequency column, you get 1 plus 2 is 3, plus 3 is 6, plus 3 is 9, plus 1 is 10. So you have 10 total people. That's your sample size. That's your N, 10. So to find your N, all you have to do is add up the F column. And that will give you your N or your sample size. In this case, it's 10. Now to calculate the relative frequency or the proportion here, what you do is take your F value and divide it by N. Our N is 10, so take your F value and put it over 10. So 1 divided by 10 is 0.1. 2 divided by 10 is 0.2. 3 divided by 10 is 0.3. 3 divided by 10 is 0.3. 1 divided by 10 is 0.1. Now, if you add up that proportion column, or what some people call the relative frequency column, if you add that all up, you're going to get 1.00 within rounding. In some cases, you might have some rounding error. Here, you don't have rounding error because it's over 10. But in some cases, you might have some rounding error. If you add everything up, you're going to get 1 within rounding error. So when I just check it here, I get 0.1 plus 0.2 gives me 0.3, plus 0.3 is 0.6, plus 0.3 is 0.9, plus 0.1 is 1. So I added up that column by P column and I got 1 or something close to 1, you'll be fine. That's what it should add up to. And then your percentage column should add up to 100% within rounding error. And all I do is move the decimal place 2 points to the right. So take that P column, multiply by 100, which means move the decimal place 2 points over to the right, and that gives you your percentage. So 0.1 becomes 10%, 0.2 becomes 20%, 0.3 becomes 30%, 0.3 becomes 30%, 0.1 becomes 10%. Add that all up, I get 100%. Very, very basic, not complicated. Discrete variable, only 5 values. Pretty simple to make this distribution. Does this tell you much? Well, it tells me that most people scored 3 or 2. Fewer people scored 5 or 1. That's all it really tells me here. Whatever that variable is that we're measuring. Most people are in the middle. And for the most part in psychology, most people are going to score in the middle of the distribution on most variables. There's going to be less people on the extremes, on the higher low end extreme. So let's check to see if we know what we're doing here. So here's a frequency distribution on the right of the screen. Determine how many subjects are in the study. Well, like I said before, to find out how many total subjects or the sample size, all I have to do is add up the F column. So add up the F column, I get 2, 6, 7, 10. So the answer is 10. Because if I add up all the F's, that gives me the total sample size, and that's A. And obviously A is the correct answer. It's 10. So to find the sample size, all you have to do is add up the F column. Now let's look at this distribution again. Is it true that more than 50% of the individuals scored above 3 in this small distribution of scores? Well, we know the sample size is 10, so let's look at it. Above 3 would mean 4 or a 5. So 4 people scored a 4, and 2 people scored a 5, so that's 6 total. Out of 10, 6 out of 10 is 60%. So 60% scored above a 3. So is it more than 60% more than 50%? Of course. So that first statement is true. More than 50% of the individuals scored above a 3 because 60% did. Now let's look at the second statement. The proportion of scores in the lowest category was P equals 3. So look at the distribution here. And you see for the value of 3, we have one individual. the frequency is 1. However, if you look at the value of 2, the frequency is 0. So that is the lowest category. Rather than 3, the lowest frequency here would be correspond to a value of 2. So the proportion of scores in the lowest category was not 3, it was 2. So that statement is false. The lowest group was corresponding to a value of 2. So let's move on to group frequency distributions. If the number of categories is very large, or if you have a large amount of data with many possible values, it's going to be impossible to list every value in the frequency distribution. For example, let's say you're looking at GPA. There's many, many, many values of GPA because it can go to the 2 or 3 or 4 decimal places sometimes, your GPA. So if you were to list all possible values of GPA, it would take up hundreds, and in some cases, maybe thousands of different values listed in the table, right? You'd have 1.00, then you'd have 1.02, then you have 1.03. Right, you could take on many different values. You'd have to list, at least hundreds of values, at least 400 values, if you were to list to the two decimal places all the GPAs. And that would be huge. That table would be gigantic. What we know about the frequency distribution table is we want to limit it to around 10 different rows of the table. So 10 different scores or intervals. If I have hundreds of different values, I can't list them all out. I'm going to have hundreds of different rows in my frequency distribution table. It's too big. So instead, I can then group things in intervals, and I can form a grouped frequency distribution. Now, this is good because I'm compacting all these values into a smaller number of categories. However, you lose information when you make grouped frequency distributions. You do not know individual scores anymore. You just know they're in a group. So let's say you have GPA and you want to group people from anyone with a GPA from 4.0 to 3.3 goes in one group, one category. That's one interval. GPA is 4.0 to 3.3. Now, do you know each individual's GPA if they're now grouped into this big category? No, you don't. You just know they're somewhere, anybody in that interval is somewhere between 4.0 and 3.3. You don't know exactly what their GPA is. That's the problem with these grouped frequency distributions is you lose individual data. The data becomes more general and less precise because you don't have individual scores. You just know they're in a range. The people in this interval have a GPA between 4.0 and 3.3. You don't know exactly what it is. You just know it's in that range. But that's what you sacrifice when you're trying to make the data more manageable. You can't list 400 different entries into your table corresponding to, every possible GPA someone could have. Imagine having a distribution table with 400 entries. You wouldn't look at it. It's not useful. There's just too many values. So by creating these intervals, you're making it easier to tell what the data kind of looks like in general. What is the shape of the distribution based on this grouped frequency distribution, this table you made. So there's pluses and minuses. You lose individual scores. It becomes a little more vague, but you also get to see the pattern better by limiting the number of values in the table. So here are some of the requirements for the frequency distribution and group frequency distributions. The intervals must be the same width. So that means if your interval is 0.5 or 1 for one interval, you got to keep it the same for all intervals. You cannot change up the interval size. The interval size must always be the same. The bottom score, the lower score in each interval, should be a multiple of the interval width. The lowest score in each interval, right? So each interval has a lower score, a lower limit, and an upper limit for your group. That's how you have a group. You have a lower limit and upper limit, right? So the lower limit has to be a multiple of the width of the interval, whatever that width is. I may tell you to make the interval a certain width. That'd probably be easier. If I'm giving you an exam, I'll tell you make the interval a set width. I'll say make the interval width of 10 or width of 5, right? However, if you're just doing this on your own, you want about 10 different intervals. So the interval width will vary to get you approximately 10 intervals. Sometimes the interval width can be large. If you have a huge range of scores, the interval width is going to be bigger. Because if you make the interval width too small with a huge range of scores, you're going to have many, many more than 10 intervals. So you want to keep the interval width the size that it takes to get about 10 intervals out of your data. And the bottom score, or the lowest score of each interval, the lower limit of each interval, should be a multiple of the interval width. These are just kind of rules, and you can see this in the text as well. This is the rules that the text is going by. And everybody has different rules for this, but we're going to use the rules that the text is recommending. In general, my rule of thumb personally is that I want between 10 and 15 intervals. But the book seems to sort of steer towards 10, so we're going to emphasize 10. So let's look at a group frequency distribution. Has categories 0 through 9, 10 through 9, 20 through 9, and 30 through 9. What is the width of the interval? Now, look at these intervals. You have 1, 2, 3, 4 different intervals here. We want to know what's the interval width. Now, if you just look at it, 0 through 9, it looks like it's 9. The interval width is 9, because 9 minus 0 is 9, 19 minus 10 is 9, 29 minus 20 is 9, 39 minus 30 is 9. So it looks like based on what's listed here, there's 4 intervals and the width is 9. However, the width is not 9. You need to also include the endpoints. So the width of the interval is always going to be one more than the highest minus the lowest here. So you always have to add 1 to the interval width if you try to subtract the upper limit from the lower limit here. And the reason why you have to add 1 is because of something called the real limit. So the real limit is really half a point lower and half a point higher than what you have here, right? So from 10 to 19, the real limits for that interval are really 9.5 to 19.5. Because anything over 9.5 is going to be rounded up into the 10 group, and anything lower than 19.5 is going to be rounded down into the 19 group. So that's why we have these what are called the real limits, because when you're dealing with continuous data or a continuous variable, you're going to be rounding up or rounding down into these intervals, into the groups. So anything higher than 9.5 gets rounded up to 10. Anything lower than 19.5 gets rounded down to 19. So when you take those real limits into consideration, the real limits for 10 to 19 would be 9.5 on the low end and 19.5 on the upper end. And if you look at the difference between those two real limits, 19.5 minus 9.5, the width then becomes 10. So although it looks like just by looking at what are called the apparent limits, 19 to 10, it looks like a difference of 9, you have to take into account the real limits. the rounding issue. So if you look at the real limits here, 9.5 and 19.5, you get a difference of 10. So in this case, the interval width is 10. It looks like 9, but it's really 10 because you have to take into account the real limits here. So the answer is 10. Don't make that mistake. Many students get confused. They say 19 minus 10 is 9, so the width is 9. But they're not including the rounding issue in the real limits, right? And if you look at the real limits, you'll know the interval width is 10 here. 29.5 in this case would be the upper limit for the interval 20 to 29. You'd have 29.5 as the upper real limit. You'd have 19.5 as the lower real limit, and the difference there would be 10. So make sure you look at the real limits and not just what's shown here, what are called the apparent limits, 29 to 20. Now that you've come up with the frequency distribution, relatively easier, and you've computed the uh, the F column and the P column and the percentage columns, you could then transform this into a graph. Your graph is going to have two axes, the x-axis, which is called the abscissa, and the y-axis, which is called the ordinate. And they generally increase from left to right on the x-axis, and from bottom to top increases on the y-axis. And you know that from graphing many times in elementary school, middle school, high school, algebra, basic algebra, right? You've done graphing, X and Y. And they meet at the at 0, 0 point, right? What's called the origin. The height of the graph, when you draw these frequency distributions, the height of the graph should be about 2/3 to 3/4 of the length of the graph. That's just a general rule of thumb. So the graphing depends on what kind of level of measurement you have. If you have a nominal variable or an ordinal variable, you're going to use a bar graph. If you have an interval variable or a ratio variable, you're going to use a histogram. So bar graph is nominal, ordinal. Histogram is interval ratio. That's the main take-home point here. And if you're doing population, you're not going to be graphing a population. I know the book talks about if you were to graph a population, you wouldn't. I mean, there'd be really no occasion where you have the population data. You're almost always graphing the sample data because you can't access the entire population, it's too big. If you're able to graph the population, what you'd end up having would be a histogram with many, many, many bars, and eventually you would smooth it out and it would become a curve. And that's why we'll be talking about different distributions, and the most common one in psychology is the normal distribution. The normal distribution is a curve. It's not really a histogram. And this point is made if you take calculus and you learn about limits. And limits start with like a finite quantity, and eventually, basically as x approaches infinity, what's going to happen? Well, the same thing is going to happen in statistics when we're graphing a frequency distribution. As the number of scores keeps increasing and you get to something along the lines of a population, the histogram will kind of smooth out and become a curve. And that's what's going on as we get to huge, huge numbers in the population. That's why you're not going to do a histogram of a population. If you have a sample, you can do a histogram. If you have a population, you're going to refer to the normal curve if the population scores are normally distributed, and they generally are in the case of things we study in psychology. And we're going to get to that because we're going to be using the Z table, the standard normal curve table, Z scores, things like that that you might be familiar with or might not. We're going to get into that, and that's going from, dealing with population data. Right now, if you have a sample, you could do your histogram, you could do your frequency distribution or group frequency distribution when your sample is relatively limited, relatively small. So to do the histogram, you need to have all the values or all the scores, and you got to list those scores on the x-axis, minimum through maximum. You need to include scores or categories that have frequencies of 0. That's very important. You can't just eliminate the interval if there's nobody in it. In order to see the shape of the distribution, you must report 0. Right? You must have the zeros in there because that's going to help you determine the shape. Sometimes you end up with something called bimodal, where you have a group of people that score really poorly and a group of people that score really well in the course. And in the middle, you have very few people or 0. So you have like what are called two peaks. You have a peak of people that scored very poorly, and you have a big peak of people that scored really highly, really well. And there's nobody in between. There's a bunch of zeros in between. And if you didn't include those zeros, you would get a distorted sort of representation of what the data looks like. So it's important that you include those zeros. Unfortunately, in a class like statistics, we do often show what's called this bimodal distribution, where you have people that it just clicks, and some of you will be like watching this or listening to it or reading the book and doing the problems, and you'll say, this is easy. This is like comically easy. Why am I, this is a joke. This makes perfect sense. This is like common sense. And then you'll have a whole bunch of people that say, this is like a foreign language. Like, I don't understand any of this. Like, I sort of trying to follow it, but it's like, I just don't get it. And that's a common scenario in statistics. So for those that, when I'm saying the stuff I'm saying and I'm talking about this stuff, it seems just very obvious and just regurgitation of things you already know, well, that's great. Then, just keep doing what you're doing and you'll be fine. But recognize that it's not like that with everybody. There's a whole wide variety of people. In statistics is that one course that kind of really separates people as far as I get it or I don't get it. It happens every semester. So if you don't get it and it's just kind of, you're really struggling with it and you're working towards it, that's fine. I mean, you just gotta have to work for it and just keep working, and then I'll be available to go through some problems and come to the office hours and stuff. And I have my sketch pad, and I'm going to be attempting to be working out problems on the sketch pad. I don't know how that's going to work because it's like it's kind of hard to use, to be honest, the sketch pad, because you write things down on this like slate and then it shows up on the screen, but your brain doesn't process the idea that what you're writing is not there on the piece of paper. It's kind of like you're writing. Imagine you were taking notes in invisible ink, and you're trying to take notes in invisible ink. You don't know what you're writing down. You don't know where you're writing it. That's kind of like how the sketch pad works to do the math problems. It's like writing in invisible ink, and you got to look at the screen to see, like, oh, well, I wrote that, and there it is. So I'm working with it. I'm gonna see how it works. If it doesn't work, I think I'm just gonna get an iPad and get Apple Pencil 2. I guess Apple Pencil 2 they use, and try it that way. Although that's a much more expensive solution because the stupid iPads are like, $800. iPad Pro, and yeah, it's an expensive solution to the problem. So I'm gonna try the Sketchpad first before we go there. But I'm gonna have something there to help you with some of the problems. I'm gonna be able to write on the screen and stuff. So bear with me. Do the problems. Read the book. Do the problems online. So there's a bunch of like sample problems online. Do that. Do the step by step. Work it at home. Write it all down. Work it out, and see how it clicks for you. And if it doesn't click and you have some questions, then we could do the office hours and talk about it. or whatever. We can talk about it somehow or another. Or I can do like sample problems and see if I can post them. It's not easy with us not being around, with COVID, and basically we're all kind of isolated from each other. It's not optimal, but we'll get through it. It's just going to require a little bit of innovation on my part and a little patience on your part. So going back to frequency distribution, you're going to draw the bars above each score. So the height of the bar corresponds to the frequency. The width of the bar just goes to the score's real limits. And we can talk about whether we want to put the intervals there, or we want to put the real limits, or we want to do the midpoint on the x-axis. I kind of prefer doing the midpoint on the x-axis. So you take the limit and you find the midpoint of the limit. So you basically add the two endpoints, divide by 2, that gives you the midpoint. And then you just plot the midpoints on the x-axis and draw the bar around the midpoints. That's probably the easiest way to do it. But the book talks about midpoints, but it also shows the whole intervals listed. You'll see in a second. So here's the simplest histogram you can have. These are discrete scores. So this is your 1, 2, 3, 4, 5 example I showed you before. And you see that there are 2 people that scored a 5. If you look at the bar, if you look over the 5, you see the bar goes up to 2. Frequencies on the y-axis and quiz scores is on the x-axis. 3 people scored a 4, so if you go to 4 on the x-axis, you look at the bar, it goes up to 3 on frequency. For 3, you had 4 people, so you see the bar above the number 3 goes all the way up to a frequency of 4. 2, you had 2, so you see a frequency of 2, and 1, you had 1. So once again, it looks like most people are in the middle. Most people scored 3 or 4 on here. Fewer people scored 5, 2, and 1. That makes sense. Most people are in the middle. This would be, if you sort of had more people here, more values, this would approach something like a normal curve where you have most people in the middle, fewer people to each extreme. Now, if you're working with a group frequency distribution, it's the same thing as we just did, except that you have the intervals on the x-axis. And this is what I was talking about in terms of labeling the intervals in the x-axis. Sometimes it takes up too much space to write the intervals. Like if you were to write 10 to 20, 20 to 30, 30 to 40 as your intervals, that takes up a lot of space on your x-axis. So instead of writing 10 to 20 as my interval limits on my histogram, I might use the midpoint. So what's the midpoint of 10 to 20? Well, to find the midpoint, it's very easy. Take 10, add 20 to 10, 10 plus 20 is 30, divide by 2, you get 15. 15 is the midpoint of 10 and 20. It's the middle point, right? The halfway point. So instead of writing 10-20, I may just write 15 and then draw the bar over 15 for that interval, because that just takes up less space on the x-axis. And then repeat it with the other interval. So 20 to 30, the midpoint would be 20 plus 30 is 50, divided by 2 is 25. The midpoint is 25. So I'd have 25. So I'd add 15 as my first midpoint. I have 25 as my second midpoint. So I don't have to list the whole intervals. I can just write the midpoints. I kind of like that. The book shows both ways. So here's what I was talking about, how messy. Look how messy it looks on the x-axis. So they're writing out all the intervals. So the first interval is 30 to 31. So they're at 30, 31 next to each other. That looks like a mess. So instead of writing the two intervals, the lower limit, which is 30, and the upper limit, which is 31, which makes it look kind of congested and messy here. So instead of writing 30, 31, I could just find the midpoint. 30 plus 31 is 61. 61 divided by 2 is 30.5. So cross out 30, 31, erase that, and write 30.5. and that would be the midpoint of the first interval. And then for the second interval, what I can do is just add 2. The second interval is going to be 32.5. The third interval is going to be 34.5. The fourth interval is going to be 36.5, and so on. And you see how if I just get rid of the intervals here and just write the midpoints, it's going to be a lot neater. It's going to look a lot better. The way you list all these intervals here, it makes it look a mess. I really don't prefer this. The book talks about both ways. I like to write the midpoints because it makes it look neater. This is my preference. Because then you don't have this really cramped kind of all these numbers kind of thrown in there next to each other like this. But if you're going to write it like, there's nothing incorrect about this. It just looks messy. If I look at the curve, the histogram here, most people scored, the majority of people here scored between 38, 39. So that interval had 6 people in it. But you have kind of, I wouldn't say multiple peaks. You have one main peak, but you have some fluctuation in the middle here. So it kind of looks like there's 2 groups here. I could say that it's kind of bimodal. You have this first group on the low end where the peak is between 32 and 33. And then you have this other group here with a peak of 38, 39. It's not super clear here how you would classify this. I would say most people are in the middle to a degree, except you have 36, 37, which is kind of low. So I could see this as bimodal having 2 peaks. I could also see it, I guess I could see it as somewhat normal. I kind of look at it more like bimodal. It kind of looks like there's 2 different groups here. Like a group of children that are relatively short, and then a group of children that are kind of taller. That's the thing with statistics is if you're looking at just like shapes and distributions, you can have ambiguous ones like this one. This one's kind of like in the middle. You don't know exactly what it is. I say it's bimodal. There's 2 peaks. Someone else might say it's kind of normal, I guess. It doesn't look skewed. We're going to talk about all this shortly, but the one thing is in real life data, there aren't super neat classifications where everyone will agree on something. And that's good because this is only just for looking at the data to see if there's anything wrong with the data or anything surprising about the data. Whether I call this bimodal or normal or skewed or whatever means nothing to the analysis. Well, I guess it can mean in certain cases that I wouldn't want to use the mean and stuff, but in most cases, it's not going to affect your outcome that much, how it's distributed. It will affect, though, your opinion of what you're measuring. Maybe you're not measuring something the best way, or maybe you're getting some really high scores from particular individuals and you want to know why these people are scoring really high on this variable. And then you could do more of an investigation. You can then look at those people and look at what they score on other variables. Maybe they're not paying attention to what you're asking. Maybe they're misinterpreting what you're asking. Maybe they're just odd in some way. But odd is good, right? An outlier sounds like a horrible thing, but a lot of times outliers are, yeah, they're bad for data analysis. Don't get me wrong. Outliers are bad for data analysis. They screw things up. But for like generating meaning of what you're doing, for just general interest in what you're studying, outliers could be very interesting, right? Why is this person scoring really high or really low? What's going on here? Let's investigate. Let's figure it out. So there's a bunch of interpretations here. It's kind of a messy example, but real life data is messy. And that's kind of part of why I'm going into this. You can also make a histogram into a block histogram. Now, this idea of block histogram that the book talks about, this is only useful if you have very few people in your sample. If you have 10,000 people in your sample, you're not going to be making a block histogram because then you're going to have 10,000 blocks. If you have 20 people in your sample, it's fine. You could have 20 blocks, right? So all it's doing is it's taking the histogram, and it's basically dividing it up. One other important caveat I want to talk about with regard to histograms. In a histogram, the bars always have to be connected. Do not separate the bars. If you separate the bars, you have a bar graph. If you connect the bars, you have a histogram. Okay, that's important. Bar graph is only useful for nominal data and ordinal data sometimes, but mostly nominal data. A histogram is useful for continuous variables such as interval and ratio data, which is mostly what we're doing in psychology. So that's just a little caveat here. As far as the blocks go, the blocks are okay if you have limited amount of data, but with large amounts of data, there's no point in having blocks. You can't, if there's so many people in the sample, you have to count the blocks. It would just be stupid. But here's an example of blocks in terms of histograms. And so all they did was they took the column and they divided it into equal portions to make it more clear. So here you can see there's 4 people that scored 4. There's 4 blocks. This is good for a small sample. But once again, if your sample's 10,000 and there's 6,571 people that scored 4, you're going to count 6,500, etc. blocks? No. In that case, you're probably just going to put on the y-axis 6,000 something and show it that way. More specifically, you're going to use a computer. You're not going to do it by hand. But blocks are, I guess they're okay. They're kind of gimmicky. You could use if you use the y-axis and you look at the y-axis, you should be able to determine what the value is. You shouldn't need blocks to know what the value for 4 is. You should be able to look at the y-axis and determine the frequency. So I would never really use blocks, but the author decides to try to simplify things by showing you blocks. I don't know. If that helps you and you have a small sample, it's fine. But you must have an x-axis and a y-axis. You cannot draw a histogram like this. You must have an x-axis and a y-axis to show your histogram. Drawing something like this is not a histogram because there's no y-axis, even if there's blocks. Must have x and y-axis. Y-axis must be frequency, x-axis must be value, possible values. And you could also have screwed up graphs. So here we have a graph on the left and a graph on the right. I'm not going to say that you're going to lie with statistics, because you really shouldn't lie with statistics. But people show things in ways to kind of get their point across. So if you look at the graph on the left and the graph on the right, they're the same graphs. They look completely differently, but they're the same exact graph. The graph on the left shows number of homicides. It looks like the homicides are out of control. Like they're just coming, they're exponentially growing. It looks like an exponential curve here. That in another couple of years, there's going to be so many homicides that we're going to have to hide in our basements. Not that we're not hiding now, because we are, but we're going to have to keep hiding. We'll never be able to come out because there's too many homicides. It's exponentially growing. So if you wanted to make a point to show that, look, it's dangerous, there's so many homicides, be careful. You show people the graph on the left. That's the be careful graph. I'm worried. This is out of control graph, right? If, however, you wanted to kind of say homicides are not a big deal, you shouldn't be worried about murders, you show them the graph on the right. They're the same graph, just shown 2 different ways. Now, neither graph is really the best way to show the graph, right? Remember I said that the height of the graph should be 2/3 or 3/4 the width of the graph. Well, that's not the case in either scenario here. On the left, the height of the graph is much bigger than the width of the graph. And on the right, they're about the same. And they're actually the x-axis is a little bit longer, but they're relatively the same. And they're kind of squished together, right? Also look at the the y-axis. On the left, the y-axis is in intervals of 2, so it goes from 42 to 44. On the right, the y-axis goes from 20 to 40 to 60. So you're compressing everything together. So if there are changes, the interval width from 20 to 40 is so big, you're not going to see those changes. Also, the graph on the right, or the squishy graph, the graph on the right starts at 0 at the bottom. The graph on the left doesn't start at 0, it starts at 40. You don't see 40 written there. But if you look at all the other tick marks, the lowest tick mark would be 40. So you're not even starting the graph on the same level. You're starting the graph on the left at 40, you're starting the graph on the right at 0. They're the same graph, it's the same data. It's just two different ways to depict it, and they're both not good ways. They're both not honest ways of depicting the data. Yes, homicide rates are going up. They're going up. That's disturbing. But they're not going up as rapidly as the graph on the left would make you think. And they're not kind of flatlined like the graph on the right would make you think. The graph on the right makes you think, it's such a minimal increase. Look at it. It's so tiny. Why are we even talking about it? It's something to talk about. It's maybe not something to be super alarmed about, but it's something to discuss and try to figure out why. And these graphs are doing a disservice. So you're going to see things like this. You're going to see this in the press. You're going to see this in journals. You're going to see. I've seen graphs like this at scientific conferences. When someone wants to make the point that they're trying to make, they'll find a graph to support their hypothesis, right? If you're trying to say homicides are on the rise and it's a big problem, you're going to show them the graph on the left. And you're not going to be lying to them, but you're going to be distorting the graph to sort of bring out or emphasize your idea that homicides need to be, addressed, and it's kind of out of control. If, on the other hand, you're trying to say homicides are not a problem, you're going to show people the graph on the right. In both cases, you're wrong because you're not giving a fair graphical representation of what's actually going on here. Now, if I want to make a frequency polygon, I'm going to list all the numerical scores on the x-axis, including those with 0 in each bin. And I'm going to draw a dot above the center of each interval. So it's basically connect the dots. Think of it this way. If you were to draw the histogram and you were to put the dot in the middle of each bar of the histogram. So if you were to put a dot on the top of the histogram right in the middle of the top of the bar for each part of the histogram, and you were to connect those dots, you would have a frequency polygon. So all you're doing is putting a dot, instead of drawing a bar, you're putting a dot corresponding to the frequency. And then you're connecting the dots. And you can do this with individual scores, and you can also do this with group frequency distributions. And this is what it looks like. Here's your frequency polygon. And this tells me similar things to what the histogram tells me is there's a spike in the middle. There's a spike here at 3. And there's not as much going on the lower end and the upper end. So, is that better than the histogram? I don't really see the need for doing the frequency polygon, but some people do it. I guess it can be somewhat neater. Maybe it's easier to construct. I like the histogram better, but you have the frequency polygon as well here. It's an alternative. And this is if you have grouped frequency distribution. So here you have the grouped intervals. And you're putting the dot here at the midpoint. So you're not listing the midpoint at the bottom, but you're putting the dot at the midpoint of the intervals. So if you look at the dot that corresponds to 4-5, that lowest category, 4-5, there's 2 people in that group. Frequency there is 2. You see how the dot is in the middle of 4 and 5, so it's at the midpoint. So they're listing all the values, and then they're putting the dots at the midpoint. Is that useful? I guess. Would I prefer them just to list the midpoints? I think if they just listed the midpoints, it would be better. I kind of prefer that. But once again, it's subjective. It's not wrong to do it this way. I just think it's easier to just list the midpoints. The bottom line is that in this graph, most people are scoring on the higher end than the lower end. You see a lot of people scoring around 10 and 11, and you see people scoring around 12 and 13, and less people on the lower end. So that's what I would take from this graph. If you have ordinal data and especially nominal data, this is all the time used for nominal data, you're going to use a bar graph. A bar graph is just like a histogram, except you don't connect them. You leave space between the bars. On the x-axis, you're going to put the categories, especially if you're doing nominal data. On the y-axis, you're going to have frequency, just like a histogram, but you're not going to connect the bars. With a histogram, you connect the bars. With a bar graph, you don't. The bar graphs indicate discrete categories, which is nominal data is discrete data. There's no intermediate values. You know, when you're graphing things like, let's say you're doing ethnicity, you're going to have Caucasian, you're going to have Hispanic, you're going to have African American, you're going to have Asian American. Those are discrete categories. You don't have in between values there. Those are discrete. And then you're going to draw a bar for each one of those groups. You're not going to connect them because there's no intermediate values. You're only going to use a histogram for interval or ratio data. You're going to use a bar graph for nominal and for some ordinal data. Although you don't really graph ordinal data that much, you're mainly using bar graph for nominal data. Here's your three personality types, A, B, and C. You see how they're discrete. You're either A, or you're B, or you're C. And there's the frequency. So this is a bar graph. The bars are not connected because this is a nominal variable. Personality type is a nominal variable with three categories, A, B, and C. And most people here are category C. If you're going to look at data and graph data based on populations, like I said before, this is very unlikely. You're going to treat it just the same as you do with a sample, except that you're not going to have the actual numbers. So for example, if you were to graph males and females in the entire country, you probably won't know exactly how many males and how many people are female in the entire country, but you will know their relative proportions. So if you have a large amount of data, your population is gigantic, like the population of this country, the US, you're not going to have values. You're not going to be able to label like, 150 million males and 175 million females. You're not going to know that, but you will know that females outnumber males by a certain proportion, small proportion, and therefore there are more females than males, and you can then graph it relative to each other. And it's going to look like this. Females score a little bit higher than males, relatively speaking. That means there's a greater proportion of females compared to the proportion of males in the US population. You won't have exact numbers because the population is gigantic. Population of the US was 360 mil. I thought it was 360 mil, something along those, 300 something mil. It's a huge population. And therefore, you're not going to get that information. I mean, you might be able to get something remotely close through the census. But as you know, the census doesn't necessarily account for everybody in the population. It doesn't. There are people that don't complete the census, right? If you don't have an address on record, you're not going to be in the census. And there are plenty of people that don't have any addresses. Or, people show up knocking at your door, you're not there, maybe you're not recorded. So even in New York City, they can't even accurately get a census of what people need in New York City because Not everyone's available. Not everyone's being able to be tracked down in New York City. So if you can't even get an accurate census in New York City, how are you going to get it in the whole country? Yeah, you have the census every 10 years. You get a somewhat decent picture of the country as a whole. But there's many people that don't end up in the census. Many households don't end up in this. Many non-households. You know, just think about homeless people. How are they? Are they in the census? So they don't exist? Of course they do. But they don't have a phone record, a phone number on record. They don't have an address on record. So when you send the census forms to their address, where do you send it? You don't. So that's just one group of people that are not in the census. And people that are impoverished a lot of times are not represented accurately in something like the census. So you're not going to have a strict numerical count of people in a population. First off, you're not going to have the population. I mean, theoretically, you could, but from a research perspective, you're not going to have access to the entire population unless you're dealing with a very limited population where there's very few people and they're all located in the same spot. And that's really rare. Even amongst rare diseases, you don't have that. So it's kind of a moot point. You're not going to have access to the population. You will have access to a sample, though. And with the sample, you can get exact numbers. With the population, you only get this relative frequency that I'm showing you here, males and females. Yes, there's more females than males. We know that. A couple percentage points higher. I don't know if that's good or bad. I guess that's good, right? That there's more females than males. There's a lot of reasons for this. I mean, life expectancy is higher for females than males. Females have a stronger immune system than males, etc. So a lot of reasons for the male population to diminish. But you're not going to have the exact numbers of females and the exact number of males. You're going to have a relative comparison here. Now, if we're talking about populations, we're not going to be doing histograms. What we're going to be looking at is our curves. Imagine this curve is just a huge histogram with just smaller and smaller and tinier categories or interval widths. And the categories or interval widths got so small for the histogram that we decided we can no longer have a histogram because the widths are so small that we're going to then just smooth it out and draw a curve over it. And that's what we have here. That's what makes up the normal curve. Now, if you look at this normal curve, it's bell-shaped. Looks like a bell. It's symmetrical, which means the left half and the right half of the curve are the same. Most people are in the middle. Fewer people are on the extremities. That's a typical of the normal curve, right? If we look at IQ, we know that the mean IQ in the population is 100. The standard deviation is 15. So most people are going to be around 100 IQ in the population. And very few people are going to be in the 130s and plus, or the 70s and minus, right? So if you're in the 70s or minus, you have a developmental disability, right? If you're in the 130s, you're considered to be in a group called Mensa if you choose to join Mensa. You're in the top, basically, 2.5% of the population in terms of IQ. But most people are in the middle. So within one standard deviation of the mean, which here is 100, you're going to have about 68% of the entire population. And we're going to talk more about this when we get to the Z-score chapter. As you saw with the normal curve is symmetrical. The majority of scores are in the middle. We know that the normal curve, the mean, the median, and the mode are the same, which we'll talk about in the chapters to come. But not all distributions are normal. Most distributions in psychology are normal, though. Most, which is a good thing, because the normal curve is easy to work with. It's the ideal distribution of scores you can have. Technically, it's called the Gaussian distribution, but we've referred to it now as the normal curve. It's just easier remembering normal curve or bell curve rather than Gaussian distribution. That's kind of one that doesn't roll off your tongue as easily. But not everything is going to be normally distributed. Sometimes you have skew, which means that there is not a symmetrical curve. You have more values or more scores in one part of the curve than the other. So you don't have most of the scores in the middle like you have with the normal curve. With the skewed curve, you have most of them either in the high end or the low end. If the tail of the distribution goes to the right, it's called positively skewed. If the tail of the distribution goes to the left, it's called negatively skewed. The best way to show this is with pictures. So if you look at this slide, the top left curve is the normal curve. You see how it's perfectly symmetrical. The top right curve is what I was talking about before. It was called bimodal. See how there's two peaks? They're symmetrical. That means the left side and the right side are the same. But there's two peaks here, so it's not normal. Normal curve only has one peak, and it's symmetrical. The two-peak curve on the top right is called bimodal. That means you have two groups in your data. That can happen. You have and unfortunately it happens in stats, like I told you. You have a group of people that they just plow through it and they're fine and it's easy for them. And you have a group of people that it's, no matter what they do, they got to keep working at it. It's a struggle and they got to work harder. Now that may not seem fair, but that's the truth in everything. Some people have it easy and some people have it hard. And if you have it hard, you just have to work harder to get through it. I wish everyone had it easy. And some people may have it easy in school and they have it hard in other parts of their lives. Right? It's not easy for everybody. Some people have it easier at school. Some people have it easier in their personal relationships, end up better. Some people have it easier in terms of their family dynamics, their health, their whatever. The point is, you have to work at it. If it's not easy for you in whatever domain of life you're in, you have to work at it. And you can get better, and you get through the course. Even if it's not easy for you, you can get through the course. I've had plenty of students that say, I'll never get through the course. I'm doomed. I'm doomed. Please have mercy on me. What they do, they worked at it again, they worked at it some more, they got through it. Right? So this is all doable for anybody. Anyone can do this course if you work at it. Then you have skew distributions. These are not symmetrical. If you look at the bottom left, you have a positive skew. See how the tail goes to the right? In the positive skew, tail's to the right. So whatever the direction the tail is, that determines if it's positive or negative. If the tail's to the right, it's positively skewed. If the tail is to the left, it's negatively skewed. You see the tail to the left on the lower right-hand side. Tail's to the left. So where would you get a positive skew? Well, a positive skew would be I gave you the first exam and everyone bombed. And a couple people got A's, but everybody else failed. That would be positive skew. That doesn't mean it's a positive situation. It just means that it's a positive skew. Most people scored on the low end, and very few people scored on the high end. That means the test was a disaster. And I probably have to curve it. That's a positive skew. Very few people did well, most people did poorly. On the other hand, a negative skew is what you want. That means everybody did well and very few people did poorly. Most of the scores are in the right-hand side, the positive side of the distribution. So as a class, you want a negatively skewed distribution of exam scores, because that means the majority of you guys did well and very few people did poorly. What you don't want the positive skew distribution, which means everybody failed and very few people did well. So you want the negative skew for the class, you don't want the positive skew. In general, neither happens. In general, the scores tend to be normally distributed. Strangely enough, normally distributed. Sometimes they're bimodal, but most of the time they're normally distributed. Very rarely are they positively or negatively skewed. And you know what? That's a good thing. I don't want a negative skew because that means the exam's too easy. Maybe I'm not really challenging you enough. You might say, well, why do I want to be challenged for? I just want to get my grade and get out of this class. Well, later on, you might want to be challenged because you're going to be challenged later on in school, later on at your job, etc. It's not just like you're not going to coast through life. The challenges are going to happen, so let's start with the challenges now. So I made the exam too easy. If it's a negative skew, it's my fault. The exam's too easy. If it's a positive skew, it's probably also my fault. The exam's too hard, or maybe I just, I didn't do a good enough job, or maybe it's just the life situations are difficult for many students, and you have to put a positive skew. Sometimes it's the student's fault, though. When the student tells me, I studied, how long did you study for the exam? And they tell me, oh, I studied for an hour. I said, really? An hour? Or how? I had some students tell me they studied for a half hour for the exam, and they failed the exam. And I said, in total, you studied for a half hour. Well, that's not going to work. You can't study for a half hour. I mean, I guess somebody can and do well. I'm not saying it can't be done, but on average, it's not a good strategy to study for a half hour for an exam. I want to see people studying for a couple weeks in advance. 2 weeks in advance. Study a little bit each day. Over time, you're going to have many hours of studying. That's probably the best way to do it, right? So these shapes of distributions are important to notice, and they also indicate outliers. So in the skewed distributions, you could have outliers. You could have really extreme scores. So for the positive skew, you might just have, most of the class is failing, but then you have one or two people and they got A's. They got like hundreds. And they just happen to maybe they took the course before at another school and never had it transferred. And they scored hundreds. Those are outliers. Why are they outliers? Because they took the class at another school and this is rehashing. They already know it. You get this a lot of times, when you have like native speakers and then they purposely fail the tests, the assessment tests, the modern language assessment tests. So, they speak Spanish at home for like their whole life, and they speak it fluently, and then they end up in like Spanish 100, and like the teacher is trying to like, teach the very basics, so like grammar and pronunciation, and you have students that are there and they're just like, yeah, this is great. Like, I know this. This is like going to be an A. And and other students are like, wow, what's going on here? So if you have only a couple of those students, you might have the positive skew distribution. So the instructor gives the exam, and the native speakers ace the exam, and all the people that are not native speakers and never spoke a word of, whether it's Spanish or Chinese or whatever, they all fail. They say, oh, this is so hard. And so then you have these outliers, and they're outliers because they had an advantage that, they already had this. They had it for many years. So you have that situation that happens where you have people that are, they have an advantage and they come in and they screw up the distribution. It happens. And so you just have to kind of examine, why is this person an outlier? And is it something about the course? Is it something about the variable I'm measuring? In research, why is this person scoring much better than everybody else? That's important to think about. That's why it's so important to look at these scores, the distributions, because it helps you as a researcher figure out what's going on. And it allows you to make changes to improve your research, or to find the students that are, gaming the system, like, failing the placement test on purpose to get easy grades. I mean, that means your placement test is not very good. You got to find a way around that. And we all know this happens. Or they don't do it with the math as much because students want to get out of math. They don't want to be taking remedial math over and over again. They do it mainly with the foreign languages because there's no remedial foreign language, and it's, they take 1 or 2 semesters of beginning language, they figure this will boost my GPA. I'm not saying it's wrong. It is what it is. It's the system they have. So until the system changes, people can do this. People can play the system how they want to play it. It's not illegal. So let's look at this curve. You see the curve here, the tails to the right. If the tails to the right is always going to be positively skewed, tail to the right. And that's the answer. True or false? It would be correct to use a histogram to graph parental marital status. Well, parental marital status is nominal. It's a nominal variable. You can either be single, married, or divorced. So that's discrete, it's nominal, and you can't have a histogram for nominal data. What you have is a bar graph. So you would not use a histogram, so that has to be false. You'd use a bar graph instead. And the second statement says it would be correct to use a histogram to graph the time children spend playing with other children. Well, now this is time. Time is continuous. Time is ratio scaled, right? So if we're using a ratio scale, we have a continuous variable, and therefore we must use a histogram. So this would be true for the second statement, and that's what it is. So hopefully this gave you just an overview of stuff, and I'll be practice the histogram stuff, the online problems and stuff. Practice that. Practice doing it by hand. You're going to be doing the online homeworks as well, so you'll have that to do. And I will be available for to demonstrate some problems through office hours, and I'll see if things work out with the graphing tablet. I will then create a couple examples and probably post them as well. We'll see how it works out. But that's it for chapter 2. Hopefully this makes a lot of sense, and I've thrown my own comments in multiple times and made this a lot longer than you probably wanted it to be. But if you have any questions, email me, come to office hours, and we'll go forward from there. But hopefully this is stuff that you can digest, and we can move forward to more interesting things in the future. Bye for now. See you next time.